Alright, so we are going to have a new lecture 19 on the flash memory. This is a key technology to build the solid-state drive, SSD. And this is a reference chapter in the textbook. And Professor Asif Khan's video. Alright, the flash memory. I think many of you are familiar with this. So you see this in your daily life. Almost every electronics will be equipped with a flash memory. And the flash memory started from the USB stick or the SD card, and you can have the capacity like 64 gigabytes. And also the flash memory is the built-in technology for the SSD, and you can have like 512 gigabytes. And nowadays you see the SSD is replacing the hard disk drive in most of the computer systems. And the flash is a non-volatile memory. Okay, so here I want to emphasize the flash is. Okay, my pen doesn't work. So it's the point. Okay, so the flash is a non-volatile memory, and that means after you remove the power supply, then the data will be there still. So you can use this for non-time data storage. This is unlike the SRAM and DRAM we discussed before. And also the flash is very high density, so you can have very large capacity. And you see that DRAM is 8 gigabyte, 16 gigabyte, but SSD you see like 512 gigabyte or even 1 terabyte these days. So the flash is built on the so-called floating gate transistor, and today we're going to discuss what is this floating gate transistor. So here is a floating gate transistor. So it's one type of transistor, like MOSFET. So here we see the MOSFET structure. You have learned that in this course. So this is cross-section MOSFET, and you have source and drain and gate, and then you have this gate oxide. So here you have the channel. So the floating gate is a little bit different. The difference here is you have additional floating gate in between this so-called control gate and the channel. And then this control gate, between the control gate and floating gate, you will have one oxide. And from the floating gate to the channel here, you have another oxide. So you have two oxides and two gates. So the gate can be typically polycrystalline silicon doped. So you can use that as a conductor. So this can be the gate. So the reason this is called a floating gate is because this blue region, this floating gate, is really floating in the circuit because you see the three terminals here, this black terminals, only attached to the source and the drain and also the control gate. For the floating gate, there is no way for you to access externally. You don't have a terminal wire connected to the floating gate. So you apply voltage only to the control gate or source or drain. You cannot apply voltage directly to the floating gate. So that's why it's called floating. Okay. So here, the floating gate transistor stores the information using the electrons stored in the floating gate. So let's say if you don't have electron in the floating gate, it stores 1. And we also call it erased state because the electrons here is erased. The other state is 0 or program state. And in this case, we are going to have the electrons stored in the floating gate. So here, this is a key difference. We rely on this electron on the floating gate or charge on the floating gate. It's similar as a DRAM, let's say DRAM. you have charge on the capacitor. And in this case, we have the charge in the floating gate. And here, if you have a charge in the floating gate, in particular, here is electron, the transistor's IDVG curve will change. Okay. So for the erased state, no electron here. If this is ID, drain current, versus the control gate voltage, is like the IDVG curve in the transistor. So this is the green line is the, let's say, IDVG for the one state, and you have a threshold voltage here. On the other side, if it's program state, you have electron in the floating gate. You will have this blue curve for the IDVG, and the threshold voltage is here. So you see that the threshold voltage is increased. So this is key feature for the floating gate transistor. It relies on the electron in the floating gate to change the threshold voltage of your transistor. And my question here is that with the electrons stored in the floating gate, why is the threshold voltage increase? You see here, right? This blue one corresponding to here. So the threshold voltage increase. So why is that with these electrons in the floating gate? So you can think this way, okay, electron negatively charged. And you apply positive voltage, this is, by the way, so the floating gate transistor always NMOS transistor. So that means the substrate is P-type, source and drain is N-type. Okay, so you want to form the channel in the NMOS transistor, you apply positive voltage on the gate, in this case on the control gate. So you want to turn on the channel, you need to do the channel inversion, right? The inversion. So you need to apply positive voltage to create the channel. But this positive voltage needs to overcome this negative charge. If you have electrons here, you need to first apply some voltage to compensate the negative charge here, electron. Or some of the positive, let's say, electric field will be shielded by this electron. You need additional positive charge on the control gate, additional positive voltage to be applied to overcome this negative charge. That means increased threshold voltage, because you need additional voltage to overcome that negative charge. So then the threshold voltage is increased. So here, this is a key conclusion, right? So the program state, electrons in the floating gate, threshold voltage increase. So this is the two states. But how do we read out the information, 1 or 0? What you can do here is to apply the, let's say, read voltage somewhere between those two thresholds. You have two threshold voltage, those two threshold voltage. But if you apply some read voltage on the control gate, which is in the middle here, like here. So if you apply this read voltage, you can measure the drain current. For the erased state, this one state, you will read out the current like this value. But for the program state, because this is smaller than the threshold voltage, you can only measure very small subthreshold current. So you can detect the difference in the drain current. For the one state, you have a large current here. For the 0 state, you have very small current. So you can rely on this current, and then the sense amplifier outside the array will detect the current and then tell you which one is 1 and which one is 0. So this is how you read out the flash memory. Any questions here? So we can take a closer look at the flash. Here, this is the detailed structure of this floating gate transistor, as we discussed. It's a MOS, and then the substrate P-type. So you have one oxide between this floating gate and the channel, and then you have the other oxide separate the control gate and the floating gate. So here, this is to write the data in. So here, let's write the data into the floating gate. Let's say we want to inject electrons from the channel to the floating gate. So this is to program the cell. Change from 1 to 0, and let's say program the cell. So this relies on very large voltage on the control gate, like 12 volts. So Flash programming is always very large voltage. Nominally, we operate the transistor in like 1 volt in the normal case, like a logic transistor. But for this Flash, we have to apply like more than 10 volts, and in this example, like 12 volts. So this is to inject the electron to the floating gate, because normally, the oxide is insulator, right? You cannot pass the current through the oxide. That means electrons cannot go through. But at a very large voltage, especially when the oxide is very, very thin, like a few nanometer, then we can have one quantum phenomenon called tunneling. So the electrons can tunnel through this oxide barrier. So I got one question. On the previous slide, did you mention that the threshold voltage is larger on the erased state? So on this slide, so the threshold voltage is larger on this program state. You see the blue one. So this is the threshold voltage. Threshold voltage is larger for the program state. Okay. So here we discuss how the electrons can tunnel from the channel to the floating gate, even though there is oxide in between. So this is purely a quantum mechanics phenomenon, and we don't want to go too deep into that. But this is something magic predicted by the quantum mechanics. If the voltage is large enough, and if the oxide is very thin, like a few nanometer, so the electrons can go through the oxide. It's like you are standing in front of a wall, separating let's say one room to another room. You have a, let's say, dry wall in between. So normally the electron, or let's say a particle, cannot go through that. But due to the quantum mechanics, if that wall is very thin, and if you have very large voltage across that, so the electrons have the probability to go through that barrier. This is due to the so-called particle and wave duality of the electron. So that means the electron is sometimes a particle, sometimes it's a wave. If you think it's a wave, then you have the wavelength of the electron, and the electron's wavelength is 13 nanometer, 13 nanometer. So that means within 13 nanometer range, you have probability to find the electron. So this is purely due to the quantum mechanics. And if you have large enough voltage, then the electrons can go through the oxide barrier. So this is different from what we discussed for the MOSFET normal operation. For the normal operation, then the electrons will not go through the oxide. So what we have there in the normal operation, if you recall the electrons, let's say the band diagram for the MOSFET from the source to the drain, and we have the source to the channel barrier, and we say that when we apply drain voltage, then the electrons will jump over the barrier. So the electron will jump over the barrier, okay? It's not through the barrier. Jump over the barrier is because of the thermal energy, kinetic energy. You have high enough kinetic energy, so you can jump over the barrier. So this is easy to understand. But this one is not jump over. This is directly go through that barrier. Or let's look at the other case. For the erase case, we can think this from the erase state. So the erase state is just the opposite to the program. You want to get the electrons out from the floating gate, out. So then you need to reverse the voltage. You need to apply 12 volts on the substrate and ground the gate. So electrons initially in the floating gate, and electrons negative charge, they want to go to higher potential, which is the substrate in this case. So the electrons will try to move out, tunnel through. So if you draw the band diagram along this vertical direction, you have this kind of band diagram. So this side is the floating gate, and this side is the substrate. And substrate is very low because you apply positive 12 volts. Positive voltage will bend down the band, and this is a barrier for that oxide, for this oxide. So electron here on the conduction band will have the probability to go through this triangular barrier, and this process is called the FN tunneling. This is for not hand tunneling, FN tunneling. So this is pure quantum mechanics phenomenon, and we are not going to discuss in details. But you need to know that which voltage to apply to program or erase. This is what you need to know. For the programming, this case, positive voltage on the control gate, electrons tunnel from the channel to the floating gate. On the other side, if you want to erase, you need to apply 12 volts on the substrate, ground the gate, and then the electrons will tunnel from the floating gate to the channel. So this is how you write the data 1 and 0 into the floating gate. Any questions? So one more thing is that we store the information as a charge in the floating gate. Why is this different from the DRAM? Let's say we store the information as a charge on the capacitor. So the key difference is the data retention time. We just discussed the DRAM, you have the decay of the charge over time because of the leakage. So DRAM cannot hold data for a long time. But the floating gate is just another case. You can store the data for a long time because normally once you have the electron in the floating gate, without this 12 volt voltage, without this large voltage, the electron will be stable in the floating gate. It can store for a long time because it's like a barrier. If you have electrons in here, then you have barrier for oxide, top, oxide down, so it will be trapped into here. So it can store a long time, like years. So that's why you can use it as a non-volatile memory. Even you remove the power supply, then your data is still there. I got another question. So for the floating gate, it doesn't need a periodic refresh. That's correct. So this is for non-volatile memory. Once you program the electron into the floating gate, it will stay there for a long time, like years, long time. So you don't need to do refresh because it's stable there. And that is because nominally the oxide will not conduct current, right? So electrons stay there. Electrons cannot go away because nominally oxide is insulating. So the electrons go in and go out must be assisted by this 12 volt very large voltage. But in the nominal case, when you do the hold operation, you don't apply any voltage, and then those electrons will stay there for a long time. All right, so this is for the floating gate. I think time is up, so we will stop here for this video clip.